The big idea that allows us to do updates in a B tree is keeping the degree variable. So basically we allow a variation in degree, which means that we can allow fusing and merging operations in the nodes. We're going to see details in a moment. In fact, B trees are special cases of an AB tree. So AB tree is denoted by two parameters, A and B. And A is that should be at least 2, and B should be at least 2a minus 1. And an AB tree will have the following properties. First of all, an AB tree is a search tree, okay? Which means that if you have a node with, say, k keys in it, so let's say E1, E2, up to EK, this node will have k plus 1 children. All the elements in the leftmost child will be smaller than E1. All the elements in the second subtree will be between E1 and E2. So sorry, this will be bigger than E1, smaller than E2, and so on. Okay, and the last will be smaller than EK. So an AB tree is a search tree where in the internal nodes we can have more than one key or more than one value stored. And the main properties are the following. First of all the leaves of an AB tree are on the same level. So these trees are balanced, completely balanced. Except for the root, all the nodes have degree between A and B. So this means that all the internal nodes will have between A minus 1 and B minus 1 elements or keys stored in them. The root will have degree between 2 and B. That's because, like, if you have B plus 1 elements, then where do you put them? You have to split them in 2, so therefore you have to allow for the root to have degree 2. Okay, but that's the only exception. And the leaves will have between A and B elements. Okay, so that's all the properties that we need to describe an AB tree. Of course, AB tree with these properties will use linear space and will have height at most log base A of n. And if we choose A and B to be within constant factor of B, the block size, then we can see that the height of the tree will be log base B of n, and we can also do a range query in T divided by BIOs. So this essentially satisfies everything that we want. Except, of course, the main thing that we haven't talked about, how do we actually update these trees? Okay, so let's take a look at that. First, we're going to look at insertion because that's a little bit simpler compared to deletion. To do insertion, first we have to do a search operation to find where this element will be inserted. Remember that these trees are search trees, so we can easily search in log base A of n time. Okay, so let's say we do a search and we find that this new element that we're going to insert has to be inserted in some leaf V. Okay, if V has less than B elements, then if we insert this into V, then B will have at most B elements, so we are fine, so we have nothing to do. So the only case where something needs to be done is when, after we do the insertion, V has too many elements in them, because remember that the leaves should have between B as A and B elements in them. Okay, in that case we do a split. We essentially walk from bottom up and we constantly split the nodes. Okay. So and then we do a following check. If a node has B plus 1 element and it's a leaf, or if it's a B plus 1 children and if it's an internal node, we just do a split node. What splitting means is that we create two copies or we create two additional nodes, V prime and double prime, and we distribute the elements of V between them. Basically something like this. In other words, if V has elements E1 up to EB plus 1, half of them, let's say E1 up to EB half, go to this one, and the rest go into that one. Okay. But this operation requires that we must add an additional key to the parent of V. the key should be such that it should be in between, so like the value of the key should be in between v and v prime. So this splitting operation requires that we insert something in the parent of v. But of course, that means that then the parent of v could overflow. The parent could have suddenly b plus 1 children. And so this operation could cascade all the way. So that's why we do it as a do loop. And as long as v, that the node that we're iterating over, has b plus 1 elements, we just go up. Once we reach the root, we will be done, because we will have split all the elements.